All right, let's go ahead and look at some of the information necessary to complete the module folder 2A pre-lab. So this one's over gravity, gravitational forces. Like the other ones, we do have a simulation, so I've opened that up in another tab so it isn't slow. And we're going to use that and some other common sense and small formulas to figure out some answers. Okay, so given what we know about how gravity works, if you throw something in the air, the Earth is going to pull it back down. So we're going to have an attractive force. Gravity wants to bring things closer together. If gravity would push things further apart, then nothing would ever stick. We'd have no solid objects, and the universe wouldn't exist. So very important that that's an attractive force. Okay, then the rest of these questions should mostly just be off of modifying the simulation. We're going to set each mass to 1 billion kilograms. So by default, they're 2 and 4 kilograms, or sorry, billion kilograms. Then we want to move to different positions. So we're going to change the separation distance over and over again. And we want to reduce the forces between masses. So we want to see what's going to make a smaller answer. So it doesn't really matter which one we move. Let's say that we're going to keep the blue one in its place and move the red one. So notice that I move it away. It went from around 4 newtons to now about 1.5 newtons. If we bring it in closer, I can only go so close because they bump into each other. But I go closer and you can see that the force is roughly about 10 times what it was a minute ago. So rereading the question, we want to find a smaller answer. We want to reduce the forces. So that would mean they need to be farther apart. Okay, so now same sort of thing. Let's set them a consistent distance apart, something like this. And we're going to adjust the masses. So change the masses. And we want to reduce the force. We want to get a smaller answer. So if you look, these are both minimized right now at 1 billion and 1 billion. If I start bringing this one up, then notice that I've got a lot bigger force now. If I bring this one up, then obviously it goes up higher. So I want to reduce these again, bump them down. And there we go. So our smallest possible answer is going to come from the smallest possible masses. That means masses need to be smaller to make a smaller force. Okay, so now we want to try to put those things together and see if we can get the smallest possible force. Well, we already said the masses need to be smaller, because once more, if I bump these up, you can see that answer grows. And then coupling that with what we learned originally, we do want these to be further apart. So we'll drag this one out here, and move that one out here, and smallest seems to be a little less than 1 Newton. So that's this one. So be careful, don't, just look at the 7. Be careful to the decimal and the zeros involved. Okay, now we want to go the opposite way, and we want to try to make the biggest force we can make. Now, constant size needs to be on, because there's potentially different answers you could have. Sorry, this one, constant size needs to be off. If I have it on, then what happens is as I make this one heavier, it stays the same size, which is what the name means, and the color gets darker, so it's like it's more dense. Whereas if that is unchecked, when this grows in mass, it also grows in size. So that's going to affect, how close these can get to each other. So we want to try to get the largest possible force. Well, obviously, bigger masses. Notice that's going higher and higher. If I move these further apart, that's giving the opposite effect on that part. So notice that there's the closest approach distance we can get. In this case, is 2.5 kilometers. That's going to give us a force of a little over 1,000. So if we go double check, looks like this one. And then we want to do the same thing again with constant size turned on. So what I want you to notice now is if I click this back on, the masses get smaller, they're more dense, and therefore we've got that darker, brighter color. But now they can be brought in closer to each other. Was 2.5, basically 2.5. Now it's about 1.25, probably some rounding error involved. But they're a lot closer to each other, and so you can see we get a much bigger force from this. In fact, now we kind of see the robots are having trouble holding these away from each other. whereas out here, they're not struggling as much. Okay, so if we look, we get an answer a little less than 4,000. So it looks like this one. Okay, so we're going to run through some questions now. We're going to get sort of a baseline measurement and a nice easy force to compare. And then we're going to make some small changes and then see what's going to happen from there. So 1 billion kilograms each. Now the constant size won't matter if it's on or off. So you can leave it either way if you like one color better than the other. I guess in this case, the size off is slightly brighter colors, but it won't matter. And then 8.2 kilometers apart. So scoot him back a little, scoot this one back a little, give her a bump here, right there. So you might see now why it's a convenient force. This combination of numbers gives us basically 1 Newton, plus or minus some rounding, but it's close enough that it just shows 1 Newton on the simulation. Okay, so now we want to make some changes. We want to change one of the masses to 2 billion kilograms. So let's take this blue one and double the mass, right? So from 1 billion to 2 billion. Notice that it was 1 Newton for the original answer, and now it's 2 Newtons. So if it's twice as big, then the way we can describe that is to say that it doubled. Then I want to reset it so I don't accidentally ruin this for the next step. Okay, so this time I want to change both of the masses to 2 billion kilograms. So if we double this one, and then be careful, make sure to also double that one. So think about it, we doubled this one and doubled this one, double or 2 times 2. I think it makes sense then that the mass being increased in that way makes the force go 4 times as bigger, which is quadruple. Now this last one, unless you've looked at the formula, which we haven't shown, and you're pretty careful and comfortable with your algebra, you might miss. So, sorry, pen glitch there. Our gravitational force is equal to the gravitational constant multiplied by 1 mass times the second mass, we'll just call them M1 and M2, divided by the separation distance squared. Now sometimes these can be uppercase, lowercase. The G is typically always uppercase, but the M's are sometimes, one big and one small, or the R sometimes is lowercase. That doesn't really matter here. And so if you think about what we just did on the other one, we changed one or both of these masses by multiplying by 2. And so it had the same effect on the answer. If I double this number only, it's going to double the answer. If I double both of these, what happens twice times 2 is 4 times the answer. Well, this time we're going to adjust the separation distance, the radius between the two objects. And keep in mind that that's in the denominator, bottom part of this fraction, and it has an exponent on it. So I want you to pause the video, think about what this might do. If we reset these, so put them back to make the 1 Newton again, and we're going to change nothing else except we're going to cut the separation distance in half. So like I said, pause it, think about what that might do, then watch the rest and see what happens. So I think that was enough time for a pause. We're not going to change the masses, but we're going to cut the distance in half. We're going to go from 8.2 to 4.1. And the answer probably didn't do what you expected. What you want to keep in mind is that that's in the bottom of this fraction. So if all the other numbers stay the same, this is what's called an inverse square relationship. It's on the bottom of the fraction and it has an exponent too. So what's going to end up happening, because of that relationship, if we change it by a factor of 1/2, that 1/2 is going to get raised to the -2 power. And so what that's going to do, the negative exponent means that you have a fraction and you're going to flip it upside down. So technically 1/2 becomes 2/1 to the second power, and then 4. So if you're comfortable with the algebra and the placement and the formulas, then you can predict that. If not, you can just try it and see. Went from 1 earlier to 4 now, and that means quadruple. All right, well, that should be it.